All right, what we're going to do now is look at an AP style free response question. This comes from the 2011 AP chemistry exam. So you can look that exam up if you'd like to see what the full question was. This question is just two parts of a larger question that we're going to go over about it's related to integrated rate laws. So this is how you might see this on an AP test. All right, so here's how it goes. A sample of ethanol gas and a copper catalyst are placed into a rigid, empty 1.0 liter flask. The temperature of the flask is held constant, and the initial concentration of ethanol gas is 0.0100 molar. The ethanol begins to decompose according to the chemical reaction shown, where CH3CH2OH produces CH3CHO gas and hydrogen gas. Of note, both the reactant and both products are gases. The concentration of ethanol gas over time is used to create the three graphs below. So you can see the graph on the left, we have the concentration of ethanol versus time. In the middle graph, we have 1 over the concentration of ethanol versus time. And in the final graph, we have the natural log of the concentration of ethanol versus time. Now on the next slide, here are our questions. Part A, given that the reaction is order 0, 1, or 2, use the information in the graphs to respond to the following. Part I, determine the order of the reaction with respect to ethanol and justify your answer. So here's something we have to note. For a 0 order reaction, a graph of concentration versus time is linear. Okay? For a first order reaction, a graph of the natural log of concentration versus time is linear. Okay? And for a second order reaction, a graph of 1 over concentration versus time is linear. So let's look at the data here. Only one of these graphs is linear, and it's the first one on the left. So in part I, we can say that this is a 0 order reaction because a graph of concentration versus time is linear. Okay? Part 2, write the rate law for the reaction. So rate, just in general, rate is equal to K times the concentration of the reactant, which is in this case CH3CH2OH, to the raised to the power or the order, which in this case it's 0 order. Anything raised to a 0 power is 1. So in this case, the rate is just equal to K. Okay? Now, part 3 says determine the rate constant for the reaction, including units. Okay, so if we remember back, a couple of ways we can think of this. If we remember back to the very beginning of this unit, we know that rate is equal to, for a reactant, the negative change in concentration with respect to time. Okay? In this case, that's the negative of the slope of this line. And that is equal to K. Okay, that's equal to K from part 2. So we just have to find the negative or the slope of the line or the negative of the slope of the line. So the change in concentration, I'm just going to pick the first point, 0.0020 minus 0.0100 over change in time, 2,000 seconds minus 0 seconds. Okay? So again, on the graph over here, I'm just picking this point and this point. Okay? So if we solve for this, we get 4.0. So the rate, let me switch pen colors back. The rate is equal to 4.0 times 10 to the minus 6th molar per second. Okay? So there's part A, 1, 2, and 3. This is a pretty comprehensive review of the integrated rate laws and rate law work. Now part B says the pressure in the flask at the beginning of the experiment is 0.4 atmospheres. If the ethanol completely decomposes, what is the final pressure in the flask? Okay. So I'm going to clear the text so I have some room to write. We can use what we know about the ideal gas law and the combined gas law from previous units to remind us that pressure is proportional to the number of moles, directly proportional to the number of moles. Okay, and so if we're in a rigid container that's volume is held constant, right, then we can look at what happens to the number of moles. And so if we look at our reaction, our initial number of moles is just 1. Okay, and our final number of moles is 2, because we have 1 mole of each product of gas. Okay, so the number of moles is doubling. If the number of moles doubles, then the pressure also doubles. So the initial pressure is 0.40 atmospheres, and that means that the final pressure will be 2 times 0.40 atmospheres, or atmosphere. So the pressure, the final pressure of the container, 0.80 atmospheres. Okay? All right, this slide is just a review of the answers from the previous slide. All of our justifications and all the work is shown in the previous slide, but just so it's all in one place. Part 1, since the graph of concentration versus time is a straight line, the order of the reaction is 0. Part 2, rate is equal to K. Part 3, K is the slope of the concentration versus time graph, so 4 times 10 to the minus 6 molar per second. And part B, by stoichiometry and using the ideal gas law, the pressure in the flask will be 0.8 atmospheres because we start with 1 mole of reactant and end with 2 moles of products, and that number of moles is directly proportional to the pressure. So we would expect that if the number of moles doubles, so does the pressure. So from 0.4 atmospheres to 0.8 atmospheres.